For our last topic regarding Gauss's law and Gaussian shells, I want to experiment with this idea of enclosed charge. So let's say we have some conducting shape, and inside this conducting shape we have a cavity. And let's say that there's no charge on the conductor, it's neutral. And I'm going to put a small charge Q inside. Now what's going to happen? Well, I'm going to get negative charges drawn towards this Q, and the negative charges charge sums to negative Q. And I'm going to have positive charges go to the outer edge they're going to go to the outer edge, and the positive charges on the outer edge sum to positive Q. Now, let's just, for our example, say that I have a Gaussian shell inside of this cavity. Well, I'm going to have an electric field in here, so my Q enclosed is just Q. And now let's extend this Gaussian shell to outside the cavity, but inside the conductor. So I'm going to put my Q enclosed inside the cavity is just plus Q. When I have the Gaussian shell inside the conductor, well, what's my enclosed shell? So when the Gaussian shell is in the conductor, my Q enclosed, well, it's going to be the sum of all the charges. So I'm going to have a plus Q, and I'm going to have to count all these negative charges, so I'm going to have plus minus Q. And that's just going to be 0. So my effective enclosed charge is 0, showing that I have no electric field inside of the conductor. And now let's extend the Gaussian shell outside. So when the Gaussian shell is outside. Oh, I guess it would be outside the conducting shape. My Q enclosed is going to equal plus Q for the inside plus minus Q for the negative charges plus Q for the positive charges on the surface, and that's just going to leave me with a total of plus Q. So I hope this helps you to see how to calculate Q enclosed when there's a mixture of positive and negative charges. Once you get the Q enclosed correct, everything follows the same for Gauss's law.